of uniform mass density, and along its axis there is a point P which is at a distance small l from this end. The mass of the rod is capital M and its length is capital L. We are asked what is the gravitational field intensity because of this mass, because of this rod at the point P. Now if we have a point mass, let's say the mass M is over here, the gravitational field intensity at the point P at a distance r is going to be gm upon r square, and it is going to be in this direction. So that is the direction of gravitational field intensity, and the value is magnitude is gm upon r square. But over here the mass is not a point mass, but it is distributed over the length. So obviously we will have to make use of integration. So what we do is, at any distance x, we take a small length dx. That is, at any general distance x, we have taken a small length dx, and the mass of this length dx is going to be dm. We know the total mass of the rod is m. M by L is going to mass per unit length, and mass per unit length into dx if we say, so this is going to be dm. That is, differential element of mass of corresponding to this length dx is going to be dm, and that is going to be m by L into dx. Obviously, if this is a rod of, let's say, 20 kg and length is 10 meter, so mass per unit length is 20 kg by 10 meter is equal to 2 kg per meter. If someone asks what is the mass of 3 meter, so this is 2 kg per meter into 3, so this is 3 meter, so it is going to be 6 kg. So when we say 20 kg upon 10 meter, this is mass per unit length, that is mass per unit length, and when we multiply by 3 meter, this is a corresponding length whose mass it has to be found out. So similarly, m by L into dx is going to be dm of this length. Now in the next step what we do is, once we have found that is the dm is m by L into dx, then because of this the gravitational field intensity over here, because of this point mass over here, let's say this is dE. So dE, differential element of gravitational field intensity over here, is going to be, we know for a point mass it is gm upon r square, so it is going to be g. What is mass of this? It is dm upon x square. It is in this direction. Or we can say dE equal to g. Dm is what? M by L dx upon x square. This is differential element of gravitational field intensity because of this differential element of mass. Because of this mass, intensity is, gravitational field intensity is in this direction, because of this it is in this direction, because of this particle it is in this direction, and so on, because of this particle in this direction. All these point masses, they will have a gravitational field intensity in this direction, so it can be directly added up. So what we can do is, we can integrate. We can integrate this from, now what are going to be limits? This is g by m L x square dx. The first particle is over here at a distance small l, and finally is at a distance L plus L. So it is L plus L integral, and we will find the net gravitational field intensity over here, which is nothing but G, M and L. We can take it out. So this comes out to be integral of dx by x square is going to be x raised to minus 2 dx, and we know we raise the power by 1 minus 2 plus 1, and the increased power comes in the denominator. That is very basics of integration. So this comes out to be x raised to minus 1 over minus 1, so it comes out to minus 1 by x. So this comes out to be minus 1 by x. Limits, they go from L to L plus capital L, which comes out to be minus gm by L. This is 1 by x, L to L plus L. And if we intend to solve it, this comes out to be minus gm by L 1 upon, first we put the upper limit, that is L plus L, minus, then we put the lower limit, that is L. So net E comes out to be gm upon L plus L into L.